Hello everyone. So today we're going to look at complex numbers in a little bit more detail. And you're going to find that the lesson today is actually very similar to the last lesson, which dealt with radicals. Similar ideas are going to be used to simplify equations dealing complex numbers as with radicals. So you'll see what I mean in a few seconds. So the first thing I'd like to discuss is complex numbers on a Cartesian plane, which is technically not a Cartesian plane. It's the complex plane. So we talked about complex numbers like a plus bi. You can actually plot these numbers on a set of axes, but you have to call the set of axes differently. We're used to calling this y and this x, okay? But in complex numbers, we can't do that because they're not real numbers. So there's no x and y coordinate. What we do instead is we call this the imaginary axis, and we call this the real axis. And complex numbers are made up of two quantities, a real part and an imaginary part. So this is the real part, and this is the imaginary part if you think of them as coordinates. So basically a becomes the x coordinate and b becomes the y coordinate, if that helps you understand how this works. So the b is in front of the I, that's the imaginary part, right? So that's going to go along the y-axis. So I'm going to show you an example of what I mean. So let's say I asked you to plot 3 plus 4i. So I'm going to use green for this one. So 3 is the real part, and 4 is the imaginary part. So the coordinate for that point would just be 3, 4. And what I do at this point is I usually say, okay, this is the x and this is the y, just to help me visualize. So 3, let's say, is around here. 4, let's say, is around here. So that would be my point on the complex plane. 5 minus 2i, I'm going to do that one in purple. So this is the real part. This is the imaginary part. So the coordinate would be 5 and negative 2. So 5, let's say, is around here. Negative 2, let's say, is around here. So I'd have a point there. So once you get past the idea that it's not an x and y axis anymore, it basically behaves like an x and y axis. The main difference is the x and y coordinates are given right in the expression of the complex number. So it's a little bit different that way, but that's how it works. Now, why would we want to do this? Well, one of the reasons we're going to see a little bit later on is this is how fractals are generated. And you might not know what a fractal is, but I'll go into that a little bit later on. Okay, so let's look at the algebra of complex numbers. And like I said, you're going to see that this is very similar to radicals. Now, if you're interested in just going in the textbook and reading about this, it's in section 2-5, page 145 approximately. Okay. So let's say I wanted you to add 6 minus 3i plus 5 plus I. Well, just like in radicals and basically in any algebra, when you're adding and subtracting, you want to combine like terms. Now this addition here basically means that this bracket could be non-existent because the number that's assumed to be in front of that bracket is a 1. When you distribute a 1 inside of a bracket, it doesn't change anything. So I can actually just eliminate all those brackets. And while I do that, I'm going to group up my like terms. So 6 wants to join with 5. And then negative 3i wants to join with positive I. 6 plus 5 is 11. Negative 3i plus I works exactly the same thing as regular algebra, which would be negative 2i. Okay, so once you get past the idea of these being complex numbers, the algebra is exactly the same as what you're used to. In a case like this, you just want to be careful about this negative because this negative is going to distribute into that bracket. So I always kind of like to still, at this, in this stage of my life, put the distributive symbols in here, that the arrows that are showing that it's jumping in, okay? Just to remind me that both of these are going to be affected by that negative 1 hiding in front of that bracket. So I would have And in this case, I'm actually going to expand that before I start to combine things, just so I don't mess anything up. So I'm going to go -1 times 4 is -4. -1 times -5i is +5i. And now I'm going to group my like terms. So the 2 and the -4 want to come together to -2, and the 3i and the 5i, -3i, sorry, +5i will be +2i. And that's all there is to it for the addition and subtraction of complex numbers. Let's look at multiplication. Again, same as regular algebra. We're going to use the distributive property here to multiply this in. We get 2i times 3, which is 6i. 2i times 4i, which is 8i squared. And this is the only thing now that we have to be concerned about, because we know that I squared is equal to -1. So we're going to simplify that a little bit further. Now, here's what's going to happen, and you can think about this in advance and write it the proper way right away, but I'm going to do it the longer way just so you see all the math, okay? You'd end up with 6i minus 8. Oops, sorry. 6i minus 8. Because I squared would become -1, and -1 times 8, which is positive, would become a -8. But this is the wrong order for a complex number. A complex number is supposed to be a plus bi, okay? So on the fly, you could have done that as you converted it, but I wanted to show you all the steps. So really the proper answer, even though our first term is negative, would be to write it as -8 plus 6i. In a case like this, as you all know, we have to use double distributivity or FOIL. I'm almost wanting students to move away from using FOIL as an acronym at this point, because when you start to do distributivity with trinomes and stuff like that, as we've seen before, it doesn't work anymore. So if you think of it as just the first number is distributing into the bracket and the second number is distributing in the bracket, I find it's just a little bit more mathematically sound. So let's do it. So 1 times 4 is 4. 1 times 3i is positive 3i. -2i times 4 is -8i. -2i times 3i will be, and I'm going to write it the long way, -6i squared. Now, once you get more comfortable with that, you can switch the sign on the fly, okay? But for now, I'm going to show all of the steps here. These two, just like any other FOIL scenario, are going to combine together. So we're going to have 4 minus 5i, and then it's going to become plus 6. And then I'm going to join the 4 and the 6 together to give 10 minus 5i. And this is the proper format of a plus bi, so we are done. Okay, so this is, again, regular algebra, very similar to the lesson from before on radicals and the operations involving radicals. What happens when we divide? Well, what did we do when we had radicals? When we had radicals, we rationalized. And that's what we're going to do here too. So we're going to use a way of rationalizing. Now for this first example, compared to the second example down here, is a little bit different. Because I just have an imaginary number on the bottom, I don't have a complex number, I'm just going to multiply by I. I'm not going to complicate things too much. I'm just going to multiply by I. You'll see what I mean in a second when I get down to that second example. And if you think of your radicals, you might already have an idea as to what we're going to do down here. But if you have just a number, a coefficient times I at the bottom, or just I at the bottom, you just want to multiply by I top and bottom like that. And what's going to happen is you'll end up with 5i at the top, and I'm going to do it the long way again, 2i squared at the bottom. Now that gives 5i divided by -2i. Sorry, -2, my mistake. There's no I anymore. But we shouldn't have a negative at the bottom of a fraction, so immediately I'm going to move that negative up to the top of the fraction, and now we are done. So how many steps can you skip without making a mistake here? Okay, because there's a lot going on. You have to know that the I squared becomes -1. You have to then know that the negative moves up to the top of the fraction. Some of you will probably be able to do that all in one step. If you can't, please show more steps so you don't lose marks. Okay. Now for this one, if we think back at our to our radical examples, what I had told you to do was to multiply the top and the bottom by the conjugate. And that's exactly what we're going to do here. Okay. What is the conjugate of the bottom? Well, the conjugate of the bottom is 1 plus 2i. And I'm going to do the same thing at the top. Now we have to put brackets because it is the entire top and the entire bottom that are being multiplied by those conjugates. Now what is going to happen when we multiply by the conjugate? Well, something very similar to what happens when we multiply a radical by a conjugate. This is technically a difference of squares, and in a difference of squares, you have the square of the first number minus the square of the second number. The O and I of FOIL, the inner and outer multiplications, cancel out. Okay? And if you don't believe me, I'm going to leave it as an exercise for you to figure that out. Okay? But we're basically just squaring the first number minus the square of the second number. So what is that going to give? And at the top, we have to FOIL. So let's just deal with the bottom first, because I want to show you what happens at the bottom. If we square, sorry, that's not very straight. If we square 1, so 1 times 1 is 1 squared, which is just 1. And then I'm going to go through FOIL with you just to show you. So 1 times 2i would be plus 2i. Negative 2i times 1 would be minus 2i. So plus 2i minus 2i gives 0. And then we have minus 2i times plus 2i. Okay? So that'll be minus 2i squared. I'm going to write it this way so we can talk about how that looks. Okay? At the top, we're going to have to distribute. So 2 times 1 is 2. 2 times 2i is plus 4i. 3i times 1 is plus 3i. 3i times 2i is plus 6i squared. So let's simplify. The top is going to become 2 plus 7i. Now, how fast can you do this? I squared becomes -1. -1 times 6 becomes -6. Right? On the bottom, how fast can you do 2i squared? So 2 squared is going to be 4. I squared is going to be -1. So I have to put that in a bracket. So let me do that off to the side so you can see what's going on. Okay? So 2i squared is 2 squared times I squared. 2 squared is 4. I squared is -1. So that becomes -4. So be very careful here. I've seen this mistake too many times in my career. There's a minus sign that came from the formula, and there's a negative sign that came from the I squared. So that gives a minus scenario. So combining and simplifying the top here, we've got 2 minus 6, which is -4, plus 7i. At the bottom, we're going to have 1 plus 4, which is 5, and that is my simplified expression. So again, just to recap, when you have a division with complex numbers in the denominator or imaginary numbers in the denominator, you have one of two choices. You can either just multiply by I to get rid of the imaginary number in the bottom, basically rationalize the denominator, or you can multiply by the conjugate, top and bottom, to get the denominator rationalized and end up with a simplified answer. Okay, we've already discussed this before. I was, planting seeds about this way back when. What happens if you try to solve a quadratic and you end up with the square root of a negative number. So if we look at our discriminant, oops, it's a t. So let's talk about the quadratic formula here. So to find our zeros, it's minus b plus or minus the square root of b squared minus 4ac over 2a. And allow me to take a second to remind you of the proof that we did of the quadratic formula, which was starting with the general form of a quadratic, ax squared plus bx plus c equals 0, completing the square with the variables, and at the very end of that, when you solve for x, you end up with the quadratic formula. Okay? Just for fun, I just wanted to remind you of that. Now, what part is the discriminant? The discriminant is b squared minus 4ac. So what is our a, b, and c for the given expression here? The a, b, and c is 1, negative 4, and plus 6. So b squared would be negative 4 squared minus 4 times a, which is 1, times 6, which is c. 4 squared, negative 4 squared is 16, minus 4 times 1 times 6, which is 24. So you can already see that our answer is going to be a negative value. That's going to be negative 8, right? Therefore, we know that we have two imaginary roots. Now, in my experience, folks, this has been the way I've seen the word imaginary simplified even in math textbooks. IM usually stands for imaginary, okay? Or complex, if you will. So let's put everything into the quadratic formula now. So x zeros is equal to negative b. So b, you can see here, is negative 4, right? So that's going to become positive 4 plus or minus the square root of negative 8, which we've already calculated the discriminant of, divided by 2a. Now a was 1, so that's just 2. So now let's use some of our techniques to simplify this. Now you do not want a decimal value, and in fact, what does a decimal value mean if you're in complex numbers anyway? You want it to be a root value if you can, if you have to, sorry. And so let's talk about what we know. Well, the first thing I would actually do this off to the side, okay? So what is the square root of negative 8? Well, the square root of negative 8 is equal to I times the root of 8. But 8 is 4 times 2. So I'm using the techniques we saw about how to simplify a root the other day, right? Can you square root a number hiding inside of 8? Well, one of the factors of 8 is 4. So that's going to come out in front as 2i root 2. So if I put that back into the formula now, I get 4 plus or minus 2i root 2, all divided by 2. Well, what do we know about things that are dividing with a plus or a minus, and this is a plus or minus in the numerator? Can you factor a 2 out of there? Okay, and for the more advanced students, if you can see that you can cross out a 2 of all 3, you can do it that way instead. But I'm going to do it the long way, so we're going to factor a 2. And then we can cross off the 2 with the denominator. So you've got your two answers, 2 plus I root 2 and 2 minus I root 2. So the last thing I'd like to talk about, and I had mentioned this before, are fractals. Fractals are from complex numbers, okay? And I've got a couple of websites here that I'd like to show you. I'm not going to show you the YouTube video. If you want to find this YouTube video on how to build a fractal, they go into a little bit more detail as to exactly how these patterns that you're about to see work. So this right here is the example of a fractal. A fractal is a geometric pattern of some sort that no matter how far you zoom into it, you never get anything but that same geometric pattern back. It's pretty psychedelic. And there are many different types of fractals. So if you look at this one here, this is one of the most known fractals. It's called the Mandelbrot set. Now I actually haven't clicked on this. I'm gonna see what happens if I click on this. So it says left click to zoom in. So if you look at the pattern, you've got all of these like circle kind of things, and then you've got this cardioid, I believe it's called, because it kind of looks like a heart. Okay, so but if you look really closely, see how you have two circles, and then it looks like if I zoom in here, I still have two circles, and if I keep zooming in, I still have two circles, and if I keep zooming in, I still have two circles. Okay, that is what a fractal is. Now the edges of the fractal look a little bit different, right? But no matter where you are, basically the pattern just keeps repeating and repeating and repeating and repeating. Okay, so even on the edge here, if I zoom in here, okay, you can see the two circles on the edges, right? So that's basically what a fractal is. Now, where does a fractal come from? Well, we're going to talk specifically a little bit about the Mandelbrot set. I don't want to spend too much time on this page, but if you go to this Wikipedia page for the Mandelbrot set, it explains to you that it comes from this equation here, Zn plus 1 equals Zn squared plus C. And I have to admit, folks, that I am not 100% comfortable with all the math. I did not do a lot of studies in university on fractals. I did talk about them here and there, and I've encountered them, but I didn't do a lot of the math. All right. So basically what they say here is images are created by applying the equation to each pixel in an iterative process. Now, iteration means doing things over and over again using previous values. Iterative and recursion, very similar ideas, okay? Meaning using a previous value to calculate a new one. And it says using the pixel's position in the image for the number C, which is arbitrarily chosen. C is obtained by mapping the position of the pixel in the image relative to the position of the point on the complex plane. So in this equation, Zn plus 1 equals Zn squared plus C, you choose a certain complex value C, okay, and it says right here C and Z are complex numbers, okay, and it can also be an imaginary number, C, and then you start to choose values for Z, okay, starting with Z0, the index 0 is equal to 0. You plug that in there, and if a certain pattern emerges, you put a dot on the picture. If a certain pattern doesn't emerge, you don't put a dot on the picture. And usually that pattern is the number you get when you do the math smaller than a specific value. And that, folks, is where I don't exactly understand how this works. It's explained down here a little bit more in detail. So if you're interested, you can go and look at it. But I don't want to mess things up, and it's going to take me too long. This is like a fairly advanced university topic. It would take me too long to research it to be able to explain it to you so that you'd really understand it. But I'm going to do my best to show you a little bit about how the math works, because I do think it's interesting. Okay. So here's the equation, Zn plus 1 equals Zn squared plus C, and that is the Mandelbrot set equation. And it says, in the example, and this is right out of your textbook, find the first three outputs of this equation, and they tell you that the starting value is z0 equals 0. Okay? So if I say z0 equals 0, that's z0 here. Okay? You're replacing n by 0. Notice that they replace the c in the equation by 2i, and like I mentioned before, you just set that arbitrarily as some complex value. All right? Now, what would zn plus 1 be? If 0 is n, zn plus 1 would be 0 plus 1, which means z1 is equal to z0 squared plus 2i. And this is what I mean by iterative process. And if you've done your ISU up to the point of the assignment that was recently given, you've done stuff like this. Okay? This is that recursive iterative process to find a value, a new value, z1, using a previous value, z0. Now, what is our starting z0? Our starting z0 is given here. z0 is equal to 0. So I'd have z1 is equal to 0 squared plus 2i, which means z1 is equal to 2i. Okay? Now, what would z2 be? z2 would be z1 squared plus 2i. And now you see the importance of putting the lines through the z's when you have z's and 2's in the same equation. Okay? So, yeah, just like z1 dealt with z0, z2 is going to deal with z1. So let's do that calculation. Now, z1, we calculated here, is 2i. So z2 is equal to 2i squared plus 2i. Now, what's 2i squared? 2i squared is 4 times i squared, which is negative 4. So z2 is equal to negative 4 plus 2i. And now all of a sudden we have a complex number as our z2. z3 would be equal to z2 squared plus 2i. And that means that we'd now have to FOIL, because z2 squared would be that, and this requires double distributivity or FOIL, okay? Which I'm going to let you, if you're interested, do on your own time. Okay? So as a quick little recap, we've basically, in this lesson, talked about how complex numbers can be mapped onto the complex plane. Mapping just means plotting. It's another way of saying that, okay? As long as you consider this to no longer be x and y axes, but the real axis and the imaginary axis. And that's basically how fractals are generated, okay? We talked about the algebra, how it's similar to radicals, adding and subtracting complex numbers, multiplying complex numbers. The main thing here being whenever you encounter an I squared, it turns into a negative 1, which, you know, does something to the equation. Dividing or rationalizing, both with just multiplying the top and bottom by I or using the conjugate, which again is very similar to what we did with radicals. Finding imaginary roots in quadratics, which we've already done before. Quickly, I kind of introduced it to you, but now you're hopefully having a better little understanding of how this all works. And we ended with this idea of fractals, okay, which you can explore more in depth if you'd like by looking at some of these websites. And that is the end of today's lesson. I will be posting some work to do in the Google Classroom. As always, if you're struggling with any concepts, either past or present concepts, there were some pretty interesting questions in yesterday's homework. So for instance, if you had trouble with the idea of how do you use these radical roots in a quadratic as their zeros, let me know, and I will definitely help you out with that. So have a great day, folks. We will talk to you soon.